Okay, hi everyone. So in this particular video, again, we're going to look at another reaction that converts alkenes into alcohols. This reaction is called a hydroboration-oxidation reaction. And what hydroboration-oxidation does is it converts alkenes into alcohols, but this time we get the less substituted alcohol as the product. So we get the less substituted alcohol as a product. And another important thing about this reaction is that we get a syn stereochemistry between H and OH. So that means you're adding a hydrogen and a hydroxyl group, and they're both syn to each other. What that means is they point in the same direction. They're added from the same face of the alkene. So I'll show you some examples, to talk about what the syn stereochemistry means, and what sort of product we're talking about. So let's first look at the examples before we go into the mechanism itself. Okay, so as an example, let's say if we have an alkene, again, more substituted carbon, less substituted carbon. When we do this reaction, this is also done in two steps, like an oxymercuration-demercuration reaction. In the first step, we react an alkene with a borane reagent, so something like B2H6. Now, you might see BH3 written instead, okay, or you might see R2BH written, okay, or you might see a BH3.THF written. But anytime you see like a borane-based reagent which has at least one hydrogen on that boron atom, relate it to a hydroboration oxidation, okay, in the situation here. So we're going to use this B2H6. We'll talk about that later, but any of these possibilities are there, okay? So you first react this alkene with a borane reagent, and in the second step, you react it with hydrogen peroxide in presence of hydroxide, okay? I forgot something in my last video. Let me point this out. This is section 8.7 in the textbook. And oxymercuration-demercuration is section 8.6 in the textbook, okay? So this is section 8.7. That's what we're talking about. Now, along with the borane here, you might see a solvent, which could be like THF, or you could see diethyl ether. These are both solvents, polar aprotic solvents that contain an ether as a functional group, okay? So B2H6 or diethyl ether. Now, since we have an alkene where there is a more substituted carbon and there's a less substituted carbon, our product from this reaction is going to be the less substituted alcohol. So that means the hydroxyl group goes to the less substituted carbon. The hydrogen is on the more substituted carbon. So that's the product that we get, okay? Let's see this in another example here. So let's say we have an example like this. We have a more substituted carbon and a less substituted carbon. So if we did BH3.THF, and this whole thing is in THF, and second, hydrogen peroxide in presence of base, sodium hydroxide. More substituted carbon, less substituted carbon. Hydroxyl goes to the less substituted carbon, so the hydroxyl would be here, and the hydrogen is going to be here. And in this particular case, we've created a chiral center now, okay? So that means this product is going to be a racemic mixture, a mixture of enantiomers. Now, I'm going to use this product and redraw this to show you what the syn stereochemistry means. So we wrote that later. So it's a syn addition. That means the H and the OH add from the same side. So that means the products that we get here, okay, the two products that we're talking about, those are going to be OH because we have the alkene. Okay, so it's a flat around the double bond. It's basically flat because both carbons are trigonal planar. So you have two faces to this alkene. So you would have an example where, one of these molecules is going to be one where the hydroxyl group and the OH, they add from one face. Okay, this is going to be one of them. Chiral center, and the where the hydrogen other phase and that's our chiral center. So what we mean by the syn stereochemistry is these two groups that were added, the hydroxyl and the hydrogen that are added to these carbon atoms, they're on the same face. They're added from the same face. Okay, so these two are syn to each other. Let's see this in a different example. Okay, another example of the syn addition, and then we will go to the mechanism that would explain the syn addition. So another example going to be this. So if you do it on a cyclic system, and we do this, say BH3.THF in THF. Second, we react this with H2O2 and hydroxide. You're going to get product where you have the methyl, This is the more substituted carbon. The bottom one is the less substituted carbon. So hydroxyl is added to the less substituted carbon. And what you can see is that both hydroxyl and hydrogen are syn to each other. And plus, you're going to get a product where hydroxyl and hydrogen are syn to each other, but they're both on wedges. So kind of notice how I've used the wedges and dashes to represent the stereochemistry. When we added the alkene, trigonal planar, so everything is in the plane here, okay? Everything is in the plane of the molecule. Now we have one situation where the addition happens from the top face. So the hydrogen and the hydroxyl are added from the top face of this molecule. That's when the hydroxyl and the hydrogen are on the wedge. And that would mean that for this more substituted carbon, the methyl should now be on a dash because it's behind the plane now, because that carbon is now sp3 hybridized. The other possibility is that the hydroxyl and the hydrogen are added from the bottom phase, okay, maybe from the front, and then the other one is from like the back. So when they are added from the back, then both hydroxyl and hydrogen are on dash bonds, and the methyl here is now on a wedge to give us that representation, you know, the stereochemical arrangement here. Okay, so now let's look at a mechanism that I would actually explain why do we get this syn addition. Okay, we'll use a simpler molecule to explain this, to understand the mechanism, okay, and explain the origin of the syn addition and why do we get the less substituted alcohol. So let's go back to this first example that we had. This alkene reacts with borane THF, let's say, or we can use B2H6 as I had in that example. Either way, it doesn't matter. Okay, so we have this in THF, and second, we're going to react with peroxide and base. So again, two steps. They have to be written as two separate steps, because if you mix all of this together, there'll be no reaction. And in this particular case, let's say this is the product that we have. We've got the less substituted alcohol, okay? So let's look at a mechanism that explains all of this. Why do we get the less substituted alcohol as a product, and why does why does it result in a syn addition? Okay. So before we go into the mechanism itself, we're going to talk about this reagent that we are using, the borane reagents, okay? So BH3, let's say, okay? So which is sort of like the simplest unit of this reagent, because you have B2H6, okay? So this is BH3, which is like half of that, so one boron with 3 hydrogens, okay? This boron here, if you were to predict its hybridization, this is sp2 hybridized, which means it should be trigonal planar, okay? And the boron has an empty p orbital on it, okay? So it is very similar to a carbocation or a carbon particle in terms of the geometry of that boron, but it is then more similar to a carbocation because there are no electrons here. A carbon radical would have an electron in that p orbital. Okay, so the borane BH3 looks like this. And as you can notice, BH3, the boron, it is sp2 hybridized and it is lacking octet, only 6 electrons, which means this boron, okay, the boron center is electrophilic, or it's a Lewis acid, okay? It's a Lewis acid. It's an electrophile, okay? It's an electrophilic site. So this is electrophilic. So very often, not very often, okay, so when you have this molecule, so what it does is, it actually exists as a dimer, okay? A dimer means this is going to combine with another one of itself. So it exists as a dimer where you have one BH3 molecule, you have another BH3 molecule, and then the electrons in this bond here and this bond here, these are shared with the other boron. And so it almost looks like the hydrogen is basically shared between the 2 boron atoms, okay? So that sort of gives 8 electrons around every boron, because now if I count octet, this boron has 4 bonds around it, or 8 electrons around it, so it's a complete octet. That boron is also a complete octet, okay? So it forms this sort of a bonding. Now this bond has a name which is called a 3-center 2-electron bond, and which if you look at any regular bond, okay? If you look at this bond here, this bond is between two atoms. So there are two centers and the bond itself has two electrons in it. So this bond here, you can say this is a two center, two electron bond. So which is a regular sigma bond. And the same is true for any other bond. If you look at this bond here, that's two centers, two electrons. So it's a two center, two electron bond. But in this particular bond, we have three centers because you have boron, hydrogen, and then a boron. And remember there, you only had two electrons. Those electrons are shared, you know, so with the other boron. So I almost want to say that we should be thinking about it like this. This electron is shared, that electron is shared, you know. So it's a bond, but it's between three centers and it only contains two electrons in it. So that's why it's called a three center, two electron bond. A regular three center bond, if you were three atoms, a regular bond should have four electrons in it. Think about this bond that we're looking at, oxygen, carbon, carbon. Those are three centers, carbon, carbon, and oxygen. So there are three centers there, and you have 2 + 2, 4 electrons. So regular three center bond should be 4 electrons, but this is a three center with 2 electron bond. Okay, and so there is sort of there's an equilibrium between these two species, you know, and it exists mostly as this dimer, okay, which is our B2H6 that we have here. So it exists as the dimer of the electrophilic, it has an anti-orbital, which would make it electrophilic, okay? And that is useful in our mechanism, okay? So now we'll go and discuss the mechanism. Again, this is not like a complete discussion on what boranes are like, but just a very simplistic view of, you know, what boranes are and how does it help understand the mechanism. Now I'm going to use this alkene, okay, and I'm going to draw it slightly differently, where I'm going to draw wedges and dashes for these methyl groups. So it means now the alkene is basically orthogonal to this whiteboard, where this methyl group is coming out and the other methyl group is going in, okay, because it's trigonal planar, so it's flat. Okay, so that's the alkene. So the alkene is nucleophile as usual. And then we have the borane reagent. So we'll use the simple unit, which is HBH3. Sorry, HBH3, not HBH3, HBH2. So it is BH3. So we'll just use the simplest unit for our discussion. And remember, this boron is electrophilic. It wants electron density. It would like a nucleophile to attack it, okay? And so the alkene is a nucleophile. So what happens is the pi bond goes and attacks the boron, okay? Because the boron is an electrophilic center. Now, if that is what happened in this step, then we should get the boron connected to the less substituted carbon, and there should be a carbocation formed at the more substituted carbon. And then once you get the carbocation, there should not be any syn stereochemistry here, okay? So what happens instead is, as the pi bond attacks that boron, one of these hydrides, it actually makes an attack on that more substituted carbon, okay? So there is, and you can imagine this as a hydride shift in some sort, a hydride shift from the boron to that carbon. And so this is a concerted process here. This is a concerted process, and this results in a transition state, okay? Now we can draw a transition state where the less substituted carbon is connected to the boron, and there was a pi bond here which attacked the boron, And since we're in the transition state, I'm using a dashed bond to say that, okay, it is part broken, part still there. That happened. The hydride is trying to migrate onto that carbon. So the hydrogen is here, and we're going to use dash bonds for all of that. So we get a transition state here, okay? This is what our transition state for this hydroboration reaction. We get a transition state. And because of this transition state, because all of this is happening simultaneously, there isn't a carbocation. What that means is the hydrogen and the boron add to the alkene from the same face. So for this particular alkene, since it's orthogonal to the plane of the whiteboard, the borane can add from the bottom face, or it could add from the top face. And plus, in this transition state, you could imagine another transition state, or like another arrangement here, where we had the alkene and the boron wanted to add to the more substituted carbon. So we'll have the boron with the hydrogen and the hydrogen here. And now the alkene attacks the boron, the hydride migrates to that carbon. And in this particular case, what's going to happen is this arrangement here, because these groups that are in the same direction, this is going to cause some steric strain. Okay, there's going to be steric hindrance between the groups on the boron and the groups on the alkene. Whereas here, we are avoiding that steric strain because these two groups are in one direction, the hydrogens are in the other direction, so that avoids the steric strain. So for that reason, the boron adopts this, or when the addition happens, it happens in this orientation, so that the boron goes to the less substituted carbon, the hydrogen goes to the more substituted carbon, and from here, essentially, this process completes. The complete transfer happens, and so what we get is a species where the hydrogen is now added to the more substituted carbon, and the boron is added to the less substituted carbon. Okay, so that gives us the addition of the borane to that alkene. And so this is all of step one. And as you can notice, the regiochemistry, that means where would the boron add, where would the hydrogen add, that is defined in this step. And the stereochemistry, the syn addition, that's also defined by this step. Okay, so that's all taken care of here, taken care of in this particular step. And then we have the second step where you react this intermediate that you made with hydrogen peroxide in presence of a base. So you do a basic second step here. And what that does is it would basically replace that borane reagent, or the BH2 part of it, although that's not how it happens, okay? It would replace that with H and OH, so that the hydroxyl ends up on the less substituted carbon. So that's how the BH2 is replaced by the hydroxyl later. So the reason I said the reason I said that's not how it happens is because this boron has two more hydrogens. That means it could go and do this process, okay, the first part, two more times. So you would get to a species where you have a boron with three of these carbon containing groups attached to it. And then the second step happens, sort of, okay? If you were to do it like in a correct stoichiometry. So every boron can convert three alkenes into alcohols if you follow stoichiometry. Okay, so that's why I said not exactly, because this is still a BH2. So that means it, before going to this step here, it can go and do this again with another alkene. And then you would have two of these groups with a BH. And then it will go again and do it again, and then you will get 3 of these on the borons. And then you would do this second step if you do it in a proper stereochemistry. So what we're going to do is this second part of the mechanism is actually there in the textbook, but we're going to skip it for now because that only shows you how the hydroxyl is replaced by the borane. There is another aspect of it with respect to stereochemistry, which we're not going to get into right now. But if you're interested, we can talk during office hours, okay? But I think in the first step, it shows us why we get the less substituted alcohol and why do we get a syn addition, okay? So both of that is from this step, okay? Because this concerted addition here, or both of those aspects of the reaction, they are controlled by this initial step. We will get the syn addition and we will get the less substituted alcohol. So that's the hydroboration reaction. We've already looked at a few examples. I don't think there is anything more. As you go through the examples, I think you're going to see this, but there isn't like anything more except for that second mechanistic detail. And I think I'm going to skip it for right now, okay? We will not go into it, but if you're interested, we can always come back and discuss during office hours. Bye.